Uh, let's see how many. We probably have 14. Okay, hopefully more will join. Well, sorry about the slight delay, which was inadvertent. Okay, now today before I come to, as I've already told you, on Facebook we have a group QEEE Mechanics. You can join this group. This is an open group, and the purpose of the group is so that if you have any difficulties, any doubts, you could put them up on the group and either me or somebody else will answer them. Also, it is encouraging. I did get some queries on I also got some queries on this thing about questions, and I have answered them to the people who have asked. So now I think there's some technical glitch. Let's try to just work it out with this. Okay. Now what I'm going to do is I wanted to start on shear force and bending moment, but before that I want to take up a very practical example. Let's do a case study in engineering where we can look at simple mechanics and see how application of proper mechanics could have helped in things. So I've just put a schematic. Let me first tell you of where this schematic is from. Those are, if you search in on websites or using some search engine, there was a failure. There's a hotel Hyatt Regency in 1981. This hotel was opened in Kansas City, and in the hotel the design of the main corridor was something like this. Let me just explain this to you, that here what we had were, there was balcony 1 and balcony 2. These two balconies were overhanging from the top, so they were being supported by these long rods. Now 2 or 3 months there were many of these rods, columns which were supporting this. There was no support from the bottom, so there was no pillar support. The support came in form of these columns from the top, and they were overhanging, and they were designed to take a particular amount of load. And one fine day, there was a day when there was a program going on, lots of people were collected on the balcony, and it so happened that the number of people, there was some band playing in this place downstairs. So people from the guests from the hotel had collected in this balcony, or the atrium, what it is called, and then suddenly these two balconies collapsed. There were about 60 people who lost their lives, and this became a major issue. And what I'm going to tell you is that what caused the failure, at least one of the reasons, was a simple fault of analysis of static forces in structures. A simple mistake was made, it was not done, and you realize after this, in the mishap of this, a lot of engineers who were responsible for designing this, they lost their licenses. So let us see a schematic of, we have shown this. So what I'm going to do is, let me show you how what the design was and what was the mistake which happened. So what we had were, this was balcony number 1, this was balcony number 2, this was to be hanging from the top, and what they had were, there were bolts. So I am just showing one column, possibly there is a series of columns like this, and the load was designed like this. So there were bolts which were holding these structures together. And as I said, at the bottom there was no support, the support was only from the top. So this was the original design. The original design was to be something like this, and then as it was expected that there would be people would be standing on the balcony, so their load would be accounted for. Now, when the actual drawings got made and when the fabrication was being done, somebody just got a brainwave saying that these columns which are shown here, let me say the column AB, either they did not have these things fabricated, they found it was too long. So what was done was that AB column was split into two. So this was the original design. In the new design or in the modified design, what was done was, let me just show the figure of the modified design, that again we have these two balconies. So this balcony was being hung from the top, and what they did was that the column which I said was split into two. So we had a column like this, and then another bolt and another column tied this up. So now in the original figure there were two columns, and in the new design, in the modified design, there were four columns. So this was the original design with two long columns, and the modified design was, which looks almost like the original design, had basically one column which would hang from the top to the first balcony, and then there were two other columns which would connect the second balcony, the top balcony to the lower balcony. So this was the difference which was made. Now what they had done was that there were bolts here. Let me call these bolts as B1, B1, that one's at the top, the bolts at the top as B2 and B2. Similarly, let me call these ones which are holding here as B1. Let me call these bolts as B2 and the bolts at the bottom as B3, and maybe let me use prime for the new design. So in the old design we had bolts B1 at the top and B2 at the top. In the new design we had bolts B1 prime which were held the top to the roof. Then we had bolts B2 prime at the top and bolts B3 prime at the bottom. Now what the person, whoever designed, the mistake they did was they kept the same bolts. So B1, B2, B1 prime, B2 prime, B3 prime were kept the same. So the original design, in the original design the bolts were designed and they were kept, and whatever B1 and B2 bolts were designed, the same bolts were kept for B1 prime, B2 prime and B3 prime. Now let us do a simple mechanics analysis of the structures. So let us look at the original design first and let us see how much bolt weight comes on each bolt, and let us do a modified analysis. So here what we had was, this was the original thing. So this was the original design, and here this was connected to the top. So what we do here is, let us have a look at, this was the original design. These bolts here were B1, B1, B2 and B2. Now let us say that the design was done for a weight W on each of the balcony. So now if we look at, if we draw the free body diagram of the balcony, I would get W here. So the load which comes on the bolt B1 is W by 2. Similarly, let me draw the lower balcony. On the lower balcony there is a weight W, and so therefore what I will get is the load which comes on bolts B2 is also W by 2. So if we had a total weight of 2W on the two balconies, it was split evenly across the 4 bolts with a load of W by 2 each. So each bolt B1, B2 was designed for load W by 2. Now as a layman, what one would think is that when we now replace this with the new design, and again if the load coming on each of the balconies is W, then we would expect each of these loads, each of these bolts to get a load of either W by 2 or less, because now we have 6 bolts. Let us see what happened. So then now when we look at the new design, that means there were 2 balconies, there was this like this, and then we had, so this was the total this thing. Now weight W is here, weight W is here. What we do is, let us cut this from the top. If I cut this from the top, then what you will see is in this free body diagram, which, so I am now taking the full structure, internal forces are not shown, I have cut this at the top. It is obvious that there is an external force of 2W. So how much is the force which is coming at the end of the column? Clearly this force is W. So now when I draw the free body diagram of column 1, I have weight W here, and so the force which comes on bolt B1 prime is also equal to W. It is not W by 2. So the force on bolt B1 prime is W. Now when I do the free body diagram of this balcony, what I will get is a load W will come from bolt B1 prime. I am doing the free body diagram of this balcony. Then there is a weight W here, and there is a load which is going to come on B2 prime, and then there is another thing B2 prime, and there is a weight W. These two W's are coming from B1 prime. So B1 primes are equal to W. So therefore what I see is the load on weight on bolts B2 B2 prime still continues to be W by 2. And a similar analysis will show the load on bolts. So what we find is, in the modified design, load on B1 prime became W, load on B2 prime and B3 prime stayed as before as W by 2. And since B1 prime was kept at the same design, that means the bolt B1 prime designed for a load of W by 2, the bolts B1 prime failed when there was an excessive load. See, that day normally it would not have failed, because we always keep factor of safety into mind when we design things. But there, on that day, there was an extra load, lots of people stood, so therefore first the load B1 prime failed, and when the load B1 prime failed, it caused to a further failure, and the whole balconies collapsed. So this is what happened, and a simple static analysis, a simple mechanics analysis, if one would have done, would have shown that when you change a design, you have to recalculate the loads, and if you don't do that, then you may end up creating a situation of a catastrophe, something like that of a Hyatt Regency failure, which should be avoided. So now let me just try to see how many colleges are there. We have 23 right now. I'll move on to a new topic, but if there are any questions on this, I would just invite them right now. Are there any queries, any doubts? Either you could type them in, or just ask them. I'll give small time. Maybe we can meanwhile try to interact with one of the, yeah, CE Pune we have already interacted before. Maybe okay, let's see CE Pune. Hello. Yeah. Did you understand? Did you follow this example? See, Pune, I will. I can see some of you. It seems like a very festive atmosphere there. Uh, um, are you following the? Like, could somebody interact with me? Can somebody come and talk? One of the students, please. Maybe a serious student. Can we get the audio? Okay, I can't get your audio. Even the video I'm not able to get. So anyway, maybe I'll continue. Maybe one more college. Uh, okay. GCT. Okay. Hello. Yeah, can you hear me? GCT. I'm getting to GCT. I can see 4 or 5 of you sitting there. Do you want to talk? Are there any queries? Any questions? Okay. Hello. Yeah. No, they don't seem to want to talk. Is yeah. Okay. Fine. Hello, ma'am.
Hello?
Yeah. Uh, who are the students who are seeing? There seems like very few students here. Or am I seeing only a very small part of the class? Hello?
Hello, sir.
Yeah, ma'am. How many people are attending the classes, ma'am?
Actually, 24 students are attending the class, sir. But today,
Okay.
sir, absent.
Okay. But are the students finding these classes useful, ma'am?
Yes, sir. It is very useful, sir.
Okay.
For that reason, only we insist the PG students also to attend this class, sir. So today,
Okay.
sir also attended.
Okay. And which department are these students from?
UG students are from mechanical department, sir.
Mechanical. Okay.
PG from the ME circle.
Okay. Great. That's very nice. Thank you, ma'am. Okay. So, okay. So now I think let's continue. Let's start with what in the textbook is chapter 7, and we'll start with a topic which is very useful in engineering. And this topic, call it as, is there somebody else who wants to talk? You can always send your request and we will immediately come to you. Now, today we will start on what we call as sectional forces in beams and members. Now, when I use the term forces, this is used in the generic sense, in the way that it will not be just forces, as you will see that this will also include moments. So what we say is, firstly, I think we have already described this before. A beam is an element whose cross-sectional length dimension is much less than the axial length dimension. For example, we have a structure like this. We see the cross-sectional length dimension is the radius and the length dimension is length L. And if R is much less than L, then such a section will qualify for a beam. That means it's an elongated body, elongated member. Now, a typical beam or a typical section like this when we have, let's first think of straight sections. And towards the end of the class, at the end of this topic, I will tell you how to extend this to non-straight members. Now we have a beam like this. Typically, this will have, as we call, it's either simply supported at the ends. What we mean by simply supported is that we represent the beam like we have, it is kept on a pin. On the other end, we keep a roller support so that we make the problem statically determinate. And on this, there is some external loading, let's say force F1, a force F2, and so on. So when we have a beam on which F1 and F2 are externally applied forces, in addition to this, maybe a couple which we show as M or M1 is also applied on the beam. Now, this couple will either come from application of two forces, then we will count them as forces, or maybe there is just a turning effect being provided on the beam at a particular point. So then we call it as a concentrated moment. Now, the ends, as we talked of, either it could be simply supported, or if we talk of a statically determinate structure, the second end is what we call as a fixed end, where the beam is fixed in the wall, and this is like this. And as you will realize, we are now talking of planar structures only. And the third type of a support, so the second end is called a fixed end, and this is also termed as a cantilever end. And the third type of support is what we call as an overhang, where the support doesn't come at the two ends, but there is some part which is overhanging the support. So these are the type of supports we usually find in beams. Now the topic which we said we'll discuss today is sectional forces. What do we mean by sectional forces? And the meaning here is, if the beam is cut at any section. So that means I have this beam, I cut at a section XX, or I cut it at a section YY. Then what forces and moments will come at the cut section? And this is what we call as sectional forces. That means actually the beam is a rigid body which is loaded, maybe at the ends, maybe with the overhang, maybe only at one end with a cantilever, whatever it is. And then what we want to analyze here is that if we make a cut at any section, at that section what forces and moments will come. And what you'll realize is, this is a very important topic, because while the loading is done at the ends, but at each section when we look at it, the section may be very close here, the section may be here, the section may be here, section could be anywhere along the beam. What we would like to know is, at the cut section, how much force comes. What is the importance of this? Why do we want to know how much force comes at the cut section? And the reason for that is because this section here should be strong enough to be able to take that force. If the section is not strong, then the beam will fail, it will break, and we don't want failures in engineering. So therefore, while the loads are applied at particular points, it is seen all over the beam. And what we have to design is, the beam should be such that it should be able to take up the force, the maximum force which comes in at any point, or the maximum moment which comes which has connotations in structural designs, it should be able to take up these forces. So that is the whole purpose of this, that we will not restrict ourselves to a particular location on the beam. What we would like to know is, I cut at a section 1, at a section 2, at a section 3, at a section 4, what are the forces and moments which come on the beam. So now before we move on, let us move and let us define some terminology. So we talk of only straight members, and we will talk of planar loading. Three-dimensional cases will not be dealt in my lectures. You can refer to textbooks if you need to do that. We will talk of straight members and we will talk of planar loading. So now if the member is straight, let us denote x as the direction of the axis of the member. So x-axis is the direction of centroidal axis of the member. What do we mean by centroidal axis? If at each section we take the centroid of that cross section, join them together, then that becomes the centroidal axis. So x-axis is the direction of the centroidal axis. Now if a member like this is loaded with some general loading, let us say there is a reaction R1, there is a force F1, and we are cutting here at a section XX. What happens at the cut section? So we have R1, we have F1, and we have cut here. I will show it with a red color. The cut we have shown XX. Now, as you know, when we cut a rigid body, then at the cut, what we get is a general force and a general moment. So this F and M, F is the general force and M is the moment at the section. Okay, because that is what happens in a free body diagram. Now because we have 2D loading, the force F, this can be written as Fxi plus Fyj, because we have plane loading, and the moment M, this can be written as M times K. That means for a planar loading, we will get 3 unknown quantities, 3 unknown or 2 unknown forces, 1 unknown moment at the cut. Now the terminology, the axis is along X. We are cutting here, so we have got a force Fx, we have got a force Fy, and we have a moment Mk. So now because axis of beam is along X, the Fx, which is the X force at the cut, this is called the normal, or sorry, this is called the, let's not use the word normal force, this is called the axial force. The force Fy, which is perpendicular to the axis of the beam, this is termed as shear force. So that is the definition of shear force. A force in a direction which is perpendicular to the axis of the beam is termed as shear force. And the moment M, which is in the Z direction, again a direction perpendicular to the axis of the beam. This is termed as, I'll just go to the top, the moment is termed as bending moment. So we have introduced three new terms today: axial force, shear force and bending moment. You make a cut at a section, if the direction, the force in the direction of the axis of the beam, that will be termed as axial force. A force perpendicular to the axis of the beam will be termed as shear force, and a moment which is perpendicular to the axis of the beam, the net direction, that is termed as a bending moment. And the names, the axial force, let's try to see the physical effect. What does the axial force do to the beam? The axial force will tend to either pull or compress the beam depending on its direction. So this is very much like a tensile or a compressive force we saw in the truss. So the role of an axial force is to provide either a tension or a compression to the beam. A shear force, well, I don't think I have a better word, it shears the beam. What do we mean by shear? If we have two things and they tend to slide over one another, that action is called shearing. So a shear force is tending to slide layers of the beam one on top of the other. So shear force, you can also think of this as a tangential force, and that is why I had earlier the word normal force for the axial force, but then I removed it because it could create confusion. So shear force is always acting, this force will act along the surface, and going by this, what does the bending moment do? The bending moment tends to bend the beam. Those of you who want to think a bit more, let me just pose some things for you. I'll not go into details. If we have a three-dimensional case, so once again I have a straight beam, I'm cutting it here, this direction is x. Now if it's a three-dimensional case, what type of force will come here? I will get a general force F at the cut section, I will get a general moment M. So now what can I say about the cut section force F? F will be equal to Fxi plus Fyj plus Fzk, and the moment M will be equal to Mxi plus Myj plus Mzk. Now which of these components? So now if I have Fx, Fy and Fz and I want to see this, so the component Fx will still be what we call as the axial force, and the component Fy and Fz, both of these will be shear forces. So now in a three-dimensional loading we will have two components of shear force because a tangent is along a plane. So on that plane we can define two mutually perpendicular directions, and these two directions, so the net shear force will now consist of force both along y and z together will form the shear force. Similarly, if we look at the bending moment, which of these components mx, my and mz will form the bending moment? Maybe let me take it up as a question to the class. So let's see, just think about it. Let's go to which one? Let's go to somewhere we have not gone. GHRC. No, there's no. Is there somebody there? No. I don't know what the status. GCT. Okay. Okay. Yeah. There are a lot of students here. Okay. Can you please tell me which of these components mx, my and mz will cause a bending moment? Which college is this? GHRCE. Yes. Could somebody respond from there? Yes. Can we get to them? Yes, please. Tell me, I have talked about these mx, my, mz. Just think about it. There is a general moment, there is a three-dimensional structure. Which of these mx, so this is x, this is y, this is z. Which of these will form the bending moment?
mx,
Which one?
mx,
mx. Okay. In the planar case, what was the bending moment component? I'll teach you some very basic things and some things which you should understand. In a planar case, the moment was bending moment was what? The moment along z, isn't it?
sir, mz, z,
So mz. So now will something be added to mz? Clearly mz should be a part of your answer. Shouldn't it be? 2D, 3D is a generalization of 2D. So if mz was there in 2D, mz also has to be there in 3D. The second component should be my, because this is also a component which is perpendicular to the axis. The axis is along x. How did we define bending moment? A component of moment perpendicular to the axis. Now, of the three x, y, z, which are perpendicular to the axis? Okay, I'll answer. Y and z are perpendicular to the axis. So these two components, they are the ones which form the bending moment. And we have, as we said, m is equal to mxi plus myj plus mzk. So these two components, they form the bending moment. And we have a special name for mxi, and this name is called the twisting moment. Do you know where does this name twist come from? How many of you are aware of the dance form called twist? Well, today we don't see that, but if you see old films, old Hindi films or old films earlier, there was a dance which was called twist. How was that dance performed? Try to visualize it in your mind. You would twist your body around the axis. So this is the version what is called twist. So what does the twisting moment tend to do? So if you have a bar like this, a component of moment like this, whose axis is along the x-axis, this tends to rotate the bar about its axis. This is called the twisting moment. So what we have defined are the three components of moments: the twisting moment, bending moment, shear force and axial force. But I'll not do 3D cases more than this. Let's come back to now the 2D loading. So what we have is, we have a case like this. We have a beam. There are some external forces, some external moments acting on the beam. We cut the section here and we want to find the shear force, the axial force and the bending moment at section XX. Now, this will be the aim of the exercise which we are going to carry out here. So you are given a beam with external supports. Now the supports, you will know the type of support, but you will not know the reaction at the support. And loading, and we have to find shear force, bending moment at any section. Now what you will find is, in most of the problems which we do, we talk of shear force and we talk of bending moment. Most problems will not talk of axial forces. And the reason for this is that most beams are loaded in a transverse fashion, which means external load is generally Fy. So if the load is only Fy, we will get only shear force. The normal force will be trivial. It will either be 0 or it will be constant in most sections of the beam. It will be, and so that is why we will talk of shear force bending moment. There's one more terminology. If we plot shear force versus distance on the beam, that means I'm plotting shear force as a distance of x. X is equal to 0 is the start of the beam. X is equal to L is the end of the beam. I show what is the shear force. So then this diagram is what is termed as the shear force diagram. If I plot shear force as a function of length on the beam, we get a shear force diagram. And similarly, if we plot bending moment as a function of length of the beam, then this graph is termed as bending moment diagram. So we have two diagrams we will talk of, shear force diagrams and bending moment diagrams. Now before we move on further, so therefore we have now, what have we done? We have defined a term called shear force, we have defined a term called bending moment, and we have seen that if we plot these shear forces all along the beam, we will get a shear force diagram and we will get the bending moment diagram. And often the engineering purpose of these diagrams is to find the magnitude of the maximum bending moment or maximum shear force, because these are what will be related to critical design elements. A section of the beam, wherever the bending moment is maximum, we have to design a beam such that it can withstand that maximum bending moment, and this maximum bending moment will also show in terms of stresses which come on the beam. Now that relation of bending moment to stresses is not a part of the first mechanics course. That we will do in the second course or in the strength of materials course. But the purpose of drawing these diagrams will often then be, first we draw a full diagram and we find the value of the magnitude of the maximum bending moment or the maximum shear force. Now let's also, in the last part of today's class, let us look at the sign convention. Now as we have seen, if I have a beam AB on which force F1 is acting, a force F2 is acting, I cut a section XX and I talk of shear force and bending moment at the section XX. What we realize is that the sign of the sectional force will depend on whether we are looking at section AX or section BX. To solve the same problem, I can either make a cut at X and look at the free body diagram of AX, that's the left side, or I can look at the free body diagram of BX, the right side. And we know the forces which we get there are equal and opposite. So now, because the signs are equal and opposite, the signs what I get from the left side are opposite, we talk of a sign convention. And first we will use V for shear force and we will use M as a symbol for bending moment. So we have shear force and bending moment and we make a sign convention. And the sign convention, with this sign convention then we just specify the shear force, and if it is positive it will imply a particular direction so that it's positive for both sides, and negative will. So now the sign convention which we follow, our sign convention follows, there are two sign conventions which we are following. I'm following a sign convention which is traditionally used by civil engineers. And what this sign convention says is, if I am looking at this is my X direction, then in a planar loading, this is the shear force. Shear force V is considered as positive if on the left cut section V points in the negative Y direction. So if V points downwards, then we call the shear force V as negative if I am looking at the right section. If I am looking at the left section. If I have a right cut, so let me show this. So this is the left cut, this is the right cut. In this left cut, so that means X is like this. This is positive V. Similarly, if I make a right cut, that means this is my beam, I make a cut here. On the right cut, a V pointing upwards is termed as positive V. Okay. So now when we write whether I take the left cut or the right cut, I will get the same sign for V. Similarly, a counterclockwise moment M is considered positive. So if I carry out my analysis and I get bending moment like this on the left cut, then this is what I will term as positive. So on the right cut, a clockwise moment will be considered as positive. So this is the sign convention which is traditionally used by civil engineers. Now we should not get bogged down by the sign convention, because if you look at some books which have been traditionally done by mechanical engineers, then for example, so there the sign convention for V is opposite. Sign convention for M is the same. For bending moment, we get the same sign convention, but they say a lot of textbooks will say if a cut section, there's an upward force, shear force on the left side. So according to this V is positive and this V is again positive. But so therefore, even if your sign conventions, so depend on the textbook which you follow. The book which we are following, that is Beer and Johnson, this convention is taken as positive for V. For textbooks which are followed by mechanical engineers, so for example, this sort of a convention you will find in a very standard book by Crandall, Dehel and Lardner, which is a book on solid mechanics that uses the convention which is put here. But even if the two conventions are different, what we will get will be just opposite signs, nothing else. So now in the remaining few minutes, let me just, I'll start with the topic yesterday, but let's just, we know the answers, how to find shear force and bending moment at a given section. How do we find these? And the basic answer to this is by equations of equilibrium or our equation of statics. So what do? We first find the forces or moments which are coming from the support. This we will get from the free body diagram of the full. This will give us the support forces. Then what we do is, so this is step 1. We find the support forces. Step 2, we draw free body diagram of the cut section. So we'll draw the free body diagram. Let's say we have to find it at section XX. I have worked out reaction R1, force F1. These are known to me. Now this R1 will depend not only on F1 but also on F2 and the other supports. So this has been determined. Now what I will do is on the cut section, V with a positive sign, I will show M. So now here V and M are unknowns, and all we have to do is we put sigma Fy is equal to 0. This will give us the value of V. We do sigma moments is equal to 0. Moments about any point is equal to 0, and this will give us the value of M. So by writing our equations of equilibrium, we will straight away get to the values of V and M. So we just have to, if we also have to find the axial force, we will use sigma Fx is equal to 0. So now the only unknowns are the forces and moments at the cut section, and they can be found out. So this is the basic methodology which we have to use to find the shear force and bending moment. In the next class, we will see how to draw shear force and bending moment for a given loading and a given beam. How do we find the shear force and bending moment? How do we draw their diagrams? With a simple, for a simple beam we will see first. Then we will see if there are complex distributions like distributed forces, etc., and so on, and how do we approach those problems. Thank you.